So, what if the most famous rule in literally all of quantum mechanics, the whole idea of superposition, isn't actually a fundamental truth of the universe? What if instead it's just this emergent illusion masking a much deeper, highly complex, nonlinear reality? Welcome to This Explainer. Today, we are unpacking a truly fascinating theoretical physics paper by Anand Aruna Kumar. It's basically a mathematical detective story hidden within what's known as the Bohm-Madelung formulation of quantum mechanics. We're going to look at how we understand quantum states, and more importantly, how they actually add together. Okay, let's dive into this. Here's our roadmap for today. 1. The quantum superposition problem. 2. The nonlinear math trap. 3. The quasi-coherent solution. 4. How linearity reemerges. 5. Slits, apertures, and interference. And finally, 6. A new quantum perspective. Section 1. The quantum superposition problem. Normally, when you look at the standard Schrödinger equation, it's strictly linear. That means if you have wave A and wave B, you can just add them together to get wave C. It's clean, it's easy superposition. But when we switch over to the Bohm-Madelung formulation, things get messy. This formulation expresses the wave function in a polar form, completely separating it into amplitude and phase. Suddenly, these equations become nonlinear and deeply coupled. You literally can't just easily add them together anymore. Section 2. The nonlinear math trap. So, in this Bohm-Madelung representation, you kind of fall into a mathematical trap. Because the amplitude and the phase are inherently coupled in these nonlinear equations, they act like two locked-in dancers. Every single move one makes strictly restricts and alters the other. You absolutely cannot change the amplitude without forcing a change in the phase, because they're guided by heavy constraints like the Hamilton-Jacobi and continuity equations. And this brings us to a really crucial quote directly from the source text. Linearity is not in general preserved at the level of amplitude and phase. What does this actually mean for us? Well, if you try to superimpose two amplitudes that are too dissimilar, they just clash violently. The resulting decoherence is so incredibly strong that basic superposition completely breaks down. They act like totally independent, incompatible systems. No way around it. Section 3. The quasi-coherent solution. Well, to fix this broken math, we have to enter what the paper defines as the quasi-coherent regime. Basically, we have to look at near-degenerate stationary branches. Simply put, we need to focus on quantum states that have nearly identical energies, where their amplitudes and phases only differ very, very slightly from a shared average. Finding this controlled environment is the absolute key that unlocks the rest of the paper's solution. This setup brilliantly illustrates the hierarchy of the math that starts to emerge. The dynamics essentially separate into two distinct layers. You've got the mean amplitude. Think of it like a heavy, guiding background current in a river, evolving according to a complex, nonlinear Ermakov penny equation. Meanwhile, the difference amplitude, which are just the tiny variations or ripples riding on top of that current, obeys a parametrically driven Matthew-Hill equation. We've effectively separated the massive, nonlinear background from the small, linear oscillations just riding over it. Section 4. How linearity reemerges. Now, here is the turning point of the entire research. Quote, despite this intrinsic nonlinearity, a linear spectral structure reemerges through a Jacobi-Anger expansion. This is the magic trick. By taking the complex, nonlinear phase modulation we established in that quasi-coherent regime and applying this highly specific mathematical tool, those familiar, easy-to-use linear rules suddenly come right back into focus. So what does that expansion actually do? It creates a Fourier-Bessel representation. Essentially, it takes the tangled nonlinear phase and generates this incredibly neat, discrete set of sidebands, which creates a square summable momentum distribution. Now, why does this matter to you? Because this mathematical shift is exactly what allows the system to admit a standard quantum mechanical interpretation once again. We have literally wrangled the nonlinear chaos back into a structure where normal quantum superposition works. Section 5. Slits, apertures, and interference. The author actually tests this by translating these wild equations into physical space, mimicking a classic double-slit style interference setup. Step 1 sets up the math in a 2D rectangular aperture. Then, Step 2 applies a parabolic slit reduction to narrow down the focus to just a single dimension of propagation.
Finally, step 3 looks at the spectral superposition of two shifted sources, basically simulating two physical slits interacting with each other in the real world. And guess what? When the math is applied to this physical slit scenario, the reduction perfectly mirrors something called Fresnel-type amplitude modulation and nonlinear phase chirp. This is a huge deal, because these exact phenomena are very well documented in the real world of nonlinear optics. Think of how light moves through fiber optic cables. This proves a theory isn't just some abstract mathematical playground. It translates beautifully and accurately to actual physical diffraction.
Section 6, a new quantum perspective. So, let's look at the author's primary conclusions. First, linearity is emergent from underlying nonlinear dynamics. Superposition is a result, not the starting point. Second, there's a strict spectral spatial equivalence. The nonlinear amplitude modulation perfectly matches the linear spectral weights. And third, translation covariance perfectly preserves the harmonic structure when you're looking at shifted sources. The really big takeaway here, in this framework, superposition is absolutely not a fundamental given of nature. It is a highly structured emergent property. Which leaves us with this final, provocative thought to end our explainer today. If superposition, the literal cornerstone of standard quantum mechanics, can be shown as just an emergent illusion of much deeper, highly complex nonlinear dynamics, what other fundamental quantum rules are just waiting to be rewritten? Thank you so much for exploring this fascinating math mystery with me today. Keep questioning the fundamentals.